This video is going to be an example of how to do calculations using the Doppler effect. So the Doppler effect, that's the one that says that the frequency we observe of a sound is going to be different from the frequency of the source due to the relative motion of the source and the observer. And we get an equation that kind of looks like a lot. Observer's on top because O comes before S. That's not Y, but it's a way to remember it. So then I want to come up with an example. Maybe I have a person who's standing still, and there's an ambulance.
Are you recording?
Driving. And it's driving this way at 30 meters per second. The ambulance makes a sound. Frequency of the source is going to be 600 hertz. And I want to know, what do I hear? So let's do this. Our observer is stationary, so we're going to have nothing there. We've got a speed of the source, and we need to decide if we are going to use a plus or a minus. When I'm standing here, there is a source that's putting out 600 hertz. It's moving toward me. If I think of this not as a sound, but in terms of like water balloons or something, this thing is moving toward me. It's shooting 600 water balloons per second. I'm going to get hit more than 600 times per second because it's moving toward me. Every time that it launches the next balloon, it's already a little bit closer to me than it was. So I expect that my observed frequency is going to be bigger than the frequency of the source. Here's frequency observed, here's frequency of the source. So what I have is that this fraction has to be bigger than 1. The top of the fraction, I can't do anything with that, but the bottom of the fraction, that's where I can do something. So I can think about this in terms of numbers. I can say maybe I've got 4 over 4 plus or minus 1. If I want this whole thing to be, the whole fraction to be bigger than 1, I want to use the minus. I'm going to use that same thought process here and say, I know that I want the minus. So now I get an equation that looks like this. Frequency observed equals frequency of the source. On the bottom of the fraction, I get V minus V source. On the top of the fraction, I get just V. And that V, that's the speed of sound. So I'm going to say that that is 340 meters per second. Then I can just plug in my values. So my frequency of the source, I get 600 hertz. And then I'm going to multiply by, on the bottom, 340 meters per second minus 30 meters per second, and on the top, 340 meters per second. And I get an observed frequency of 658 hertz. It is a shift from what the source is. I'm moving at about 10% of the speed of sound. It's a noticeable shift. It's about a 10% shift. So this makes sense. I want to do another example. Let's say I've got another person here who is running away fast from this ambulance. And we'll make them some kind of a superhero so that they can run really fast. I'm going to have them moving at 20 meters per second. Again, frequency observed, frequency source, V plus or minus V observer, V plus or minus V source, and now I've got both going. If I've got just the observer moving, so I'm going to ignore the motion of the source for a moment. If I've got just the observer moving, I'm moving away. I expect that what I get because of moving away from the source is that my observed frequency is going to be lower than my source frequency. In order to get that to be lower, if I'm only able to mess with the top of my fraction, I'm going to need a minus sign. So let's do that. The top of my fraction becomes a minus. Now I want to look at just the source. So ignore that the observer is moving, ignore all this part. Just the source. If the source is moving away from my observer, then I expect that I'm going to be getting hit less than 600 times per second, right? I'm going to get a lower frequency. In order to get a lower frequency, I need the bottom of my fraction to get bigger, so I'm going to need a plus. So the bottom of my fraction will get a plus, and now I can plug in my numbers. I've got still 600 hertz for the frequency of my source, 340 minus 20, and on the bottom, 340 plus 30, and I should notice a pretty big difference here, and what I get is 519 hertz, which is a big difference. Last thing, I can also use this to find a speed if I don't know what that speed is. Let's say I am standing here and there is something moving toward me. It's going to be just a box with a speaker on it, and it'll be on wheels. I know that my source frequency is 400 hertz. But what I hear is 430 hertz. So I would like to know the speed. I'm going to start with my same equation. Frequency observed, frequency of the source. I've got V plus or minus V source plus or minus V observer. That's my basic equation. I know my observer speed is 0. And because this is moving toward me, that means I know that this whole fraction has to be bigger than 1, which means the bottom of my fraction is going to have to be a minus sign. I am trying to find the speed of the source. So I've got this equation. I can multiply V minus V source times frequency observer equals frequency source times the speed of the wave. I can divide by frequency observer. And then solve for Vs. And now I can plug in some numbers. I get this 340 meters per second times 1 minus the frequency of the source is 400 hertz. The frequency observed was 430 hertz. and I get a speed of 23.7 meters per second. So I can solve this equation in both directions. It's not terribly difficult. It's just walking through the different pieces. And this is what we actually use in all sorts of different ways to determine the speeds of unknown objects relative to us. We use a different version of this in astronomy with light, but it's the same idea. That's it. That's a Doppler effect example, or a few of them.